Welcome to my video on the preview of the book General Relativity by Leonard, Susskind, and André, Cabannes. This is part of the Theoretical Minimum series. I just ran across this at the bookstore this week, and I have not read this book yet. I've gone through and read it, so I'm not an expert on this material. But I did want to show you the book because I think it's kind of an interesting concept the way they've done this. This Theoretical Minimum, there's like 4 books in the series, and it's all on physics, but it kind of introduces you to the subject, gives you some mathematics and some conceptual idea. It's a 2023 book, so it's fairly recent. And then here's the chapters. I'm just going to kind of briefly touch on some of this. I'm not going to go into gory detail. The equivalence principle and tensor analysis, tensor mathematics, flatness and curvature, geodesics and gravity, metric for gravitational field, black holes, falling into a black hole, formation of a black hole, Einstein field equations, and gravitational waves. All pretty weighty subjects. This is not for the faint of heart. And I did find one sentence in here that one paragraph I thought especially, this is this second author, this Cabannes, whatever. This describes himself, and it kind of follows me too. I belong to a group of people to whom these so-called continued study courses are intended. Individuals who studied physics at undergraduate and sometimes graduate level when they were students, then did other things in life, but kept an interest in science and would like to have some exposure to where physics stands today at a level above plain vulgarism. Now, he uses the word vulgarism. I call this conceptualization. Those are books that don't get into the mathematical details, but they describe it conceptually or in words. Indeed, personalized, I have always found vulgarization more confusing and hard to understand than real explanations with some equations. And I agree with this sentence. The books that give pure concepts are harder for me to understand because I know mathematics. Okay, the first lecture is divided into 10 lectures. And each one of these starts off with this conversation between Andy and Lenny. It's kind of interesting. And that kind of breaks down the subsections. This is the equivalent principle and tensor analysis. Okay, tensors are a form of mathematics. They're one step above vectors, basically. That's kind of a simple way of describing them. But they are used to describe very complex systems, and that's why it's used in general relativity. So you can see there are some equations in this book. Definitely, this is not an introductory book. If you're not familiar with some basic mathematics like calculus and some vectors, then you're not going to like this. It's not for you. That was chapter 1. Now I'm going to go to chapter 2. This is more on tensor mathematics, and here's our little conversation. And this goes into more of the mathematical detail of what a tensor is and how you manipulate them. I just studied these slightly in undergraduate and graduate school in physics, but I didn't get into much. They're not, it's more of an advanced topic, but they are covered some. So a lot of diagrams and equations and they give you some exercises in here. I'd like to see the results of these worked out. And then chapter 3 is on flatness and curvature, because you're talking a lot about space. And space has curvature, or it can be flat. It depends on the way you mathematically represent it. Yeah, and this is, when I was a young physicist in the 1960s, general relativity was a bit of backwater in theoretical physics. Partly this was because the technology for detecting the subtle non-Newtonian effects mostly did not yet exist. But also physicists like myself were also interested in the fundamental aspects of the subject. So this is pretty much what I've seen too, is back when I was in graduate school back in the 80s. This was a very interesting concept, but it didn't have very practical uses, so it really wasn't emphasized other than just a neat curiosity, a fact of nature. And so chapter 4, geodesics and gravity. This goes into more of gravity and the geometry of space-time. Here's some of these tensor equations. You'll have to learn that. My impression of just going through this book, kind of leafing through it and reading selected parts of it, is you can go through this book, but you're going to have to spend some time. This is not a light read. This is not something you're going to do on a Sunday afternoon in an hour. You're going to have to spend some time. This is what I call a slow read book. In other words, it's going to take some time. It's not It's not a skim read book. You're going to have to really spend some time probably to look at some other material if you don't get halfway familiar with what this is, because it's fairly dense, but not as dense as, say, a normal textbook would be. That's what I liked about it was I think I can get a feel for the subject, some level of depth without going through multi-semester courses on General Relativity, which I don't have time for. It goes into black holes. That's one of the big theoretical concepts, and they're starting to see those now and detect them quite a bit, so it's becoming much more observationally validated on the black hole. And then it talks about falling into a black hole, what you'd experience going into one, and it's really, of course, it would tear you apart. They call it spaghettification. It talks about Schwarzschild metrics, the event horizon, and singularities. These are some of the concepts when space and time converge. And then formation of a black hole, how are black holes formed? Goes through the basic the diagrams on that and try to help you understand that a little bit. How space and time collapse due to gravity. Light doesn't escape from a black hole. Too much gravitational force exceeds the escape velocity that light can get out of. Then this gets into the Einstein field equations. This really all goes back to about 1910, 1915, when Einstein was doing a lot of work on this. And so it's a lot of his work plus others' work past them. And let's see, this is just for his basic equations. Riccati tensor and curvature scalar, just different aspects of this, more detail. And then this goes on gravitational waves. These are ripples in space-time, and I think they were first detected they've been theorized for years. I think they actually detected one, I think in 2015. I think it was like two giant black holes collided or something. I forgot the whole details, but they have been verified. So this is the book. I just wanted to show it to you in case you want to start looking at this. Again, I'll give you an idea. It's not a conceptual light read book. It's more of a book you're going to have to spend some time with and really dig into it if you want to understand the subject. But if you like general relativity, kind of like I do, I'm going to try to get a little more involved with this and get a little smarter on the subject. Well, I hope you got something out of this and learned a bit about it. The back talks a little bit about the scientists involved that did this. And there's also some other YouTube videos on this. Leonard Susskind, I watched a few of his videos. They're kind of helpful. All right, well, thank you for watching. Hope you learned a little bit about this book. And I wish you well. Good luck. Thank you.